Hey friends, welcome back. Today we're going to be looking at the problem 2-sum. 2-sum is a LeetCode easy style question that generally most people won't have too much difficulty solving, but especially if you're relatively new to programming or you're not super strong in your algorithmic skills, this is definitely something that could throw you for a loop. So today we're going to break down this question, we're going to look to see what ways we can optimize it, and we're going to come up with a solution that would hopefully be something that would be accepted in a technical interview. So let's go ahead and let's take a look at the first example here. So we have a list of integers. We have 2, 7, 11, and 15, and we are expected to be able to come up with something that will be able to sum to 9. So let's first think about some way that we could brute force this, for example. One approach we could probably take here is we could probably use a for loop, and we could start over at the 2 here. We could have a nested for loop that will start at index I plus 1, for example, which in this case here would be at 7. And what we could do is we could compare the 2 pointers to one another to see if they match. So in this case, we're going to run into the solution right away, but we'll assume that we don't. So at the start here, we'd say, okay, so 2 plus 7, does that equal 9? Yes or no? So again, in this case, the answer is yes, so that's our 2 indices that we would end up returning, but let's say that it's not. Okay, so then we would just simply take our pointer here, and we would move this over to the 11. So then we would come back here and we would say, okay, 2 plus 11, does that equal 9? Let's say that then. Okay, so then 2 plus 15, does that equal 9? Nope, okay. And then as we move forward here, we'd eventually find ourselves in a position here where we'd be moving our blue pointer over to 7, and then we just kind of iterate over here. So the red at the end of the 2 would be over on the 15, and then we just come back and we'd reset it over at the 11, and then we'd have the pointer at the 15, and we continue working our way through until we're at the final index here, right? So now we have our first pass to the solution here. Let's go ahead and let's think about the time and space complexity. So in terms of the time complexity, we said that we wanted to have a pointer that would start at the first index, and we want to check the remainder of the array to see if we have its complement. And so what that means is we'll be iterating through the array once, just to get our first index, or to get the first value of our addition here, and then we would be populating the second through another O of n loop that's going through the remainder of the array. So our naive solution here is going to have an O of n squared time complexity, and we're not going to be using any extra space in this solution, so our space complexity in this case is going to be O of 1. Okay, so now let's see what we have here. We have an O of n squared runtime algorithm. That's probably not going to be something that's going to work super well inside of an interview, so we'll probably want to look to optimize this. So let's think here. What's the bottleneck that we're running into? Well, the thing that's really slowing down our runtime complexity right now is that we need a more efficient way to check to see if a complement to the value that we're looking at exists in the array that sums to our target. So we need to figure out some more efficient way to check to see if the complement is going to exist in the array. And so in order to see if that complement exists, we need to be able to get its index. So we need to ask ourselves, what's the best way that we can maintain a mapping of each element in the array to its index? And the answer to that is a hash table. A hash table should be really good for this purpose because as long as we have a well-chosen hash function, we should be able to get an amortized O of 1 runtime. Now what a hash table is going to allow us to do is it's going to allow us to remove that inner for loop that we're doing, going through the remainder of the array to populate the second part of the addition statement. We'll be able to reduce that runtime from O of n to O of 1, so we'll be trading a little bit of space for speed. The impact that'll have is it'll be able to reduce our overall algorithm's runtime from O of n squared down to O of n. So now we've identified that we want to use a hash table. How can we go ahead and properly implement this? One solution that we could go for would be to iterate over the entire array once, populate all the values inside of the hash table, and then we can iterate through the array again to check to see if the complement of the value that we're looking at exists elsewhere within the hash table. That would likely be a very good solution inside of a coding interview and would be able to move you past the round. It would get us down to that O of n runtime. One way we can look to optimize that a little bit more would be to think about what's actually happening as we iterate through the entire array. So like for example, instead of saying that this is a 9, let's go ahead and let's say that this is let's say it's 18. Just so that way we don't run into the solution right away. Okay, so now we've identified that we want to use a hash table. Let's go ahead and let's think about how we can implement that in a way it's going to make sense. So what can we use for our key value pairs? Well, what we want to do is we want to return the indices, and we want to be able to look up the indices of the values based on the complement of the value that we're looking at compared to 18. So what that means in this case is that our key could be the complement, and then our value in this case would just be the index that it is that particular value is at within the array. So if we go ahead and we run through this, I'm just going to write the keys. We can see the indexes just by referring to the value in the array. If we initially just populate the hash table with all the values in the array, just iterating through the array once, that would give us 2, 7, 11, and 15. And then we'd be able to check to see if the complement exists by saying, okay, well, let's say we already gone through 2 and now we're sitting at 7. So we can say, okay, 18 minus 7, that value is 11. 11 exists in our hash table, therefore we want to find the indexes associated with this 11. And then we return that with the index that we're at in our array up here. Now that is definitely a solution that we could go with and would probably work, but there's a little bit of a slightly more optimized way that we can go about solving this. And that would be, rather than populating this hash table right away and having to iterate through the array twice, we can iterate through the array once. And what we can do here is essentially what we were doing before, but we can say, okay, let's start at 2. Let's compare 18 minus 2. 18 minus 2 is 16. Do we have 16 anywhere in our hash table? No, we don't. Okay, so we'll put the value that we have here at the index 2. So then we move over to our 7 here. We say 18 minus 7. 18 minus 7 is 11. Do we have 11 in our hash table anywhere? We don't. Okay, so we'll just go ahead and add 7 to our hash table. Then we get over to our 11, which is where we're going to find our solution. And we say, okay, 18 minus 11, that's 7. Does 7 exist in our hash table? It does. And then whenever we put the value in the hash table itself, we also store the index, so we can return the index that's associated with 7 along with the index that we're currently at in the array for the 11. So in that case, we'd be able to come up with a solution. So let's go ahead and jump over to code and see how we can implement this solution. Okay, so here we are over in the code. So let's go ahead and real quick just write out the first test case that we had, just that way we have it to reference. We have 2, 7, 11, and 15 with a target value of 9, and we wanted that to return the indexes 0 and 1. Okay, so let's think about how we can go ahead and solve this now. So what's the first thing that we said that we wanted? The first thing we said we wanted here was a hash map with mapping an integer is our key and an integer is our value. We'll just call that map, new hash map. And we said that we wanted to iterate over the entire array, so let's go ahead and throw in our for loop here. Is less than nums.length I++. And what we need to do here is for each value we need to figure out what the complement is. So we have our complement, and that's going to equal the target minus nums at the index that we're at. So then what we want to do is we want to say if our map contains the key for the complement that we're looking at, we want to return a new array, and inside of that array, there we go, inside that array we will return map, and then we'll get the complement, and then we will also return the value that we're at for I. And then if we didn't get through this, we're still running through our algorithm, so we'll go ahead and just update our map and put the value inside of there. So we'll put the value and then the index itself. And then if we get down to the bottom, we can assume that we didn't find a solution, so we can just return null. Alright, and there we have it. Let's go ahead and submit our code and see what we get back from the submission. Alright, and look at that there. Runtime 2 milliseconds faster than 92% of submissions. Memory usage 45.7 megabytes. Better than a solid amount as well. Looks like we have a pretty solid solution there. If you'd like to learn how to tackle one of the problems that's listed here, go ahead and click on the video that's on your screen, or you can check out the playlist listed right below where you can see my solutions for all of the LeetCode questions that I've done up to now. I'll see you guys in the next video where we tackle another LeetCode problem. Thanks for watching, guys.